So in this video, we are going to cover the breadth first search algorithm. So here the BFS is going to be with respect to tree in this session. So if you are the person who actually finds this kind of tough or afraid how to solve this, then with the end of the session, I promise that you'll feel it's so easy and you'll be able to solve n number of important problems just by knowing 10 lines of code. So just by modifying the 10 lines of code, you will be able to solve n number of important problems, right? Now let's deep dive into the session. So before we get into all the problems which actually involves the BFS, so as many of you would know, BFS is also called as the breadth first search, and this is one of the very important algorithm, right? So now let's first discuss about the general steps which is used. So whenever you actually know that it's going to be BFS, then right away you should know it's going to be Q. Why we are using Q is something you will understand. So you know that Q actually follows the first in first out principle, right? And in this, we'll process each level. So first we process the first level, second we'll process the second level, and third we'll process the third level. As we are processing first level first, second level second, and so on, so it kind of follows the first in first out principle, right? Also called as the FIFO principle. So therefore, we are using the Q, right? So now let's see how we are using the queue. Okay. So first a queue is used and the root is added to the queue. Then what will happen is you will have an outer loop as well as an inner loop. So the loop will run, the outer loop will actually run till the queue is empty. That is till all the inner nodes are processed, right? And then in the inner loop, what we will do is we'll process all the nodes at current one level. So first we'll process the ones at the current level. And then as a part of this processing, we will add the next level nodes to the queue, right? So therefore, these nodes can be processed in the next iteration of the outer loop. So thus, if you try to summarize it, the outer loop will run once per level and the inner loop will run to process each node at the current level and also to push the next level of nodes, right? So that is what we will do it. So I will also get to the part where you actually see the coding, so it will make much more sense. So, but this is something you should know. You should be very, very clear with it. You can take a sample problem. We'll take the next problem which is there. And then you should actually try to understand this very clearly and be very clear with the template so that you're able to do the other problems, right? Okay. So we are covering around 8 problems. So these go from easy to medium and then to the hard level. But you don't have to become intimidated by the problems. If you understand the crux of the BFS really well, then in that case, it becomes very easy to solve all this problem. You will be able to make tiny changes and then you can solve all these problems in no time, right? Okay. So one thing is that before we get into the problems, there are two things which you should keep in mind. That is, you will have to pause every time you go towards a problem. Okay. So the first thing is I would advise you guys to pause and understand the problem statement. So first take some time out, understand the problem statement before you get to the modification of template. So in that way you understand what this problem is, very important. And the second step is to, after you understand the problem explanation, right, pause and then understand how the template, so basically this will be our template, right? So these general steps is modified to accommodate this particular problem. So instead of associating every solution or logic to a particular problem, if you understand the BFS template clearly and understand how it's modified for every given problem explanation, then you will be able to master this topic very easily and solve many of the tree problems, right? So two things you have to keep in mind. First thing, whenever you start with a problem, understand the problem statement clearly, take a moment, understand it. And the second thing is take another moment and understand how the actual template is modified, how the do BFS template is actually modified to support this particular problem, right? Okay, so with that, let's get into the first problem. So this is a very basic problem and it's called as binary tree level order traversal. So given the root of a binary tree, return the level order traversal of its nodes values. So basically they're saying that when you're given the root of a binary tree, you will have to return the level order traversal. Level order traversal is nothing but breadth first search. So it's an other name. So whenever you hear the name called level order traversal, which is nothing but going from left to right level by level, that means you know it's BFS. Let's go through this example. So the root is 3, but the first level is 3. Second level, if you go from left to right, it's 9 and 20. Third level, again, when you go from left to right, it's 15 and 7. So basically, we have a 3, a 9 and a 20, and a 15 and a 7. So therefore, you have a level order traversal. Now, let's get to the main part. Understand this problem very clearly. So if you actually go through this problem, right, this will be like the core template, and then many other problems will follow it. Okay. So we are given a main function where you have the level order and then given a root, right? Okay. So what are we doing? We're just checking if the root is null or not. This is a basic null check. And you would return the empty list because I'm creating a rest list because that is the output which is being required here. And then we are having a queue. Why are we having a queue? We know if it's going to be BFS, then it's going to be a queue. So we are creating a queue, adding the root to the queue, and then we are doing a BFS to the queue, and at last we are returning the result. That's it. So if you see, this function is very pretty straightforward. So if you try to understand, you're doing a null check, creating a queue, and then doing a BFS and returning the result. That's it. This is very simple, and this is something you will do for every other problem. But depending upon the input as well as the output required, you would make the necessary changes. Now let's get into our main function, do BFS. So we are getting a queue, and then at this part we are getting a list because the output has to be a list of integer. So basically, if you see, every level they want it as an individual list. So 3 is a list, 9, 20 is a list, 15, 7 is a list, right? So as we know the steps, now go back and think about these steps, okay? Even write this down somewhere. So that is very, very clear to you. So a queue is used. We saw that. Root is added to the queue. Yes, we saw that in the main function. After that, what we'll have? We'll have an outer loop for the which will iterate till the queue is empty, and then an inner loop to process the nodes in the current level as well as in the next level, right? Okay, so you can write this down, write, understand it and write it out in your own words. Now let's see how we do it. So we're having an outer loop, right? Right. So this loop will iterate till the queue is empty. So basically to process all the nodes in the level. So basically in the first case, only the root will be added. So only the nodes which is present in the first level would be there. Then we are creating a list, okay? I'm creating a list because this specific question wants the output for every level in a list. So we are creating a list. And then we are running the inner loop which runs for the size of the queue. So these are all very straightforward. So what happens in the inner loop? We actually pull the node from the queue, and then I am adding it to the list because this is what is required in this question. And then if the left is not null, we are adding the left child and the right child. In a tree, if you see, there is only a parent to child relationship. There is no child to parent relationship, right? So when you process the nodes in a particular level, you push their children into the queue so that it can be processed for the next level. Once each level is over, so the inner loop is for one each level and the outer loop is for the whole tree. Once each level is over, we are adding it to the output list. That's it. So this one is the first variation where you're outputting out, where you're giving the result as output as a list to the thing. So this is like a very basic BFS, which you should be clear about. It, I would advise you guys to understand this very clearly, write it down, take this example, trace through it, like dry run through the problem, understand it, and even rewrite this code many number of times. Now let's try to understand how this worked. Okay. So we had a queue, we created a queue in the main function, we put 3 into the queue. And then we actually had a 9 and a 20, right? So when we had the 3 in the queue, the outer loop would have started when the 3 was there. Then after that, we would have gone to the inside the first level. So the first level 3 would have been pulled out by the queue, and then 3 children 9 and 20 would be the part of queue. That's it. One level is over. Again, the outer loop will check if the queue is empty. It won't be empty because it'll have 9 and 20. Then it will go inside the inner loop. In the inner loop, 9 will be taken out, but there are no children. Okay. In the inner loop, 20 will be taken out. There are children. So 15 and 7 will be added to the queue. And thus the inner loop will exist at this time. So inner loop corresponds to the particular level, and we are also pushing the next level into the queue for next processing. So the outer loop would again check if the queue is empty or not. It won't be empty because it has a 15 and a 7. And then the inner loop will process 15 and 7, add it to the list, and then send it. That's it. So might seem intimidating in the beginning, but I would advise you guys to dry run this process in a piece of paper and then understand how this works. Okay. Now, take a moment and then understand how the template has been fit, whatever the steps what we discussed in the beginning, how it has been fit for this problem. So this is the basic BFS or the level order traversal. In the upcoming problems, just by making some modifications on this logic, we will solve it. Right? Now let's get to the next problem. Maximum depth of a binary tree. Okay. Given a root of a binary tree, one second, yeah, return its maximum depth. Okay, so they want you to return a maximum depth. First, let's try to understand what is maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from the root node to the farthest leaf node. Oh, okay. So basically, they want the depth. For example, this would be depth would be 2, but then the longest level means then in that case the depth would have been 3. So basically, if you try to see it from the perspective, see to solve any most of the tree problems, you have to do a tree traversal, right? And you can either do it in a DFS way or you can do it in a BFS way. So if you see it in a BFS way, that means we have to go level by level. And if we actually count the number of levels, then that will give us the maximum depth. That's it. So what we will do, we have the same piece of code just like the before function. We are doing a null check, creating a queue, adding the root to the queue, and calling the BFS function. 3 steps always. Null check, create a queue, add the root to the queue, 4 steps, and then call the BFS. Right? Now in the BFS function, what are we changing? Same thing. So we have the queue, and then the queue would have the root. We are processing the queue, and then we are having the size of the queue and iterating through the nodes in the queue. So in the inner loop, we are processing through the nodes in the current level. After we process the nodes in the current level, we are pushing its children to the queue. Why are we checking if the current left is not equal to null? This is because if it's null, and then if you try to access current of left or current of right, it will result in null pointer exception, right? So to prevent that, we are checking beforehand if it's going to be null or not. That's it. So each level is processed. So every time the inner loop runs for a level, for example, the first level is over, then we are incrementing the count plus plus. So we know the first level is over. And then when the second level happens, we are going to increment count plus plus. The third level, we are going to increment count plus plus. So if you see the difference between the level order traversal ka basic BFS and this is that there we used a list because we had to output all the elements in a level to the list. And here, instead of a list, we are just having a count variable and counting the number of levels. That's it. Very, very simple, both these problems. You can take the solution, understand this problem, try to code it, understand the level order traversal, code it, and then put it together side by side and understand how similar they are, not much difference at all. We're just counting the number of levels here, and there we actually output the elements which were present in each level. That's it. So here again, take a moment and then understand how the template has been modified and how this problems has become very easy to get solved, right? Okay. Now let's get to the next problem. Binary tree right side view. Given the root of a binary tree, imagine yourselves standing on the right side of it. Okay. So you have to imagine yourself standing on the right side of it. Return the values of the nodes you can see ordered from top to bottom. Okay, so you have to stand on the right side of it and return the value of the nodes you can see ordered from the top to the bottom. Okay, so basically what they're saying, imagine a person standing this side, okay? And if you want the thing from the right side, that means the output for this they're saying is 1, 3, and 4, right? One second. Right. Okay. So if you imagine a person is standing this side, that means you would have to output the elements which are able to be seen from this side. So if you try to understand this problem clearly, then it will occur to you that each level they just want the last element. That's it. So basically, you can do a level order traversal or BFS, and instead of giving all the elements in a level as an output, we are going to only add the last element as an output. Does this ring a bell? Isn't this a very, very small modification of the first problem what we had? Let's dive deep into it. Same thing, we're doing a null check. creating a queue, adding the root, calling the BFS. So the only thing which changes is in the do BFS. See, this is why writing the code as functions is very, very helpful. If you think about it, the logic which was present here, the only thing which changes is the input or the output depending upon the question. And in the do BFS, you just have to make tiny changes based upon the question. So if you put all this piece of code in the main function, then it becomes hard for you to track when the code grows large in size. And also, if you want to debug, then it's very hard when all large number of codes is inside single function, right? Especially writing in functions like this helps debugging very, makes it very easier. So please do have this habit. So in this BFS, again, we have a queue. We are having the list integer output because they want the list as an integer. So we are having an outer queue as usual, and then which will run till the queue is empty. Okay. And then you have the size of the queue. Let's get into this. Then we have the processing each nodes in the queue. So we are going to start with the inner loop. So therefore, for the inner loop, you will start with current level. So we'll have the inner loop. As usual, we are going to process all the nodes in the current level as well as push the nodes which is present in the child, right, in the next level to the queue so that they can be processed on the next iteration. Okay. So what are we doing at the difference? So in the BFS, naturally, we used to add all the elements to the list. But in this case, they only want last element. So we are adding only last element to the list. Why are we initializing a tree node current outside? Because if I initialize it inside, then it cannot be accessed outside the loop, right? Because it will become a local variable. The limit of this variable will be only within this loop. So in order to avoid that, I'm just initializing this outside so that I can add the last node's value alone to the list. That's it. So in a normal BFS, we'll add all the elements to the list, but here I'm adding only the last node's value to the list. So again, take a moment and then put this solution also, understand this problem, write the solution, and then keep all the three solutions side by side and understand how this changed from the previous problem. So if you understand how this PFS works, then when you come across a new problem which you have never seen before, you would be able to guess how to use this to solve the problem. Now let's get to the next problem, is to find bottom left tree value. So till now we saw all the variations where we accessed all the elements level by level, and we actually used a list to output the elements. So for the count, we used a count plus plus, else we use a list, right? Okay. Now let's try to understand this problem. Given the root of a binary tree, return the leftmost value in the last row of the tree. So in the last row of the tree, if they ask the rightmost value, it's very easy, right? Whatever we did, instead of us adding the current dot value at each level, once the outer loop is processed, then we can add it only the last one, which will be the current of value. That would give us the rightmost value. But now they want leftmost value. Okay, let's see how we can solve this problem. We are starting with the traditional main function, where again we have a queue and then we are doing a null check, adding the root. So here we are not having any list because it's not required. So now we are going to do a BFS. As usual, we have an outer loop to check if the queue is empty or not, and then the inner loop to iterate through our nodes in a current level. And then we are going to process it. Okay. So when we process it, there is a small change. Usually, how do we process? We go from the left to right. And as Q follows the FIFO principle, therefore, in that case, what will happen? You will first process all the elements in the left and then you will process all the elements in the right. So you will be left with the rightmost element. But as here you want the leftmost, we are processing all the right first and then the left second. So the last element you will be left with would be the leftmost element. That's it. So if you try to understand this logically, whenever you get the 2, instead of pushing 1 and 3, that means the last element in the level would be 3. We are pushing 3 and 1. So when you finish processing this level, the last element you would be left is 1. So even if there are 5 levels, at every level, the last element you will have is the leftmost value. So it's very easy, and this is a template where you're pushing the order as right left instead of left and right. There might be another way to solve this problem also, but this is a slight tweak on the classic BFS which you know. Okay. So in this case, it's written iterating through the nodes in the current level. Yes, just making a small change. Right. Okay. So now let's get to the problem. So if you feel it already gets too much at this point, take a moment back and then understand how the first three corresponded to his first template and the second one was a bit changed from the second template. So we have covered four problems till now. Take your time, try to solve it, and then you can start continuing with the next four problems. So let's get into this part, populating next right pointers in each node. So you're given a binary tree where all the leaves are on same level and every parent has two children. Okay. So every parent will have definitely two children. Okay. Populate each next pointer to point its next right node. So basically what they're saying is for every node, we are also having a value called next, just like how the linked list has, and then we have to point this one to here. Okay. So if you see, we would have to point this child to this child. So from here, I would have to point their siblings. So among the siblings, and then from two's child to three's child, five to six, and then six to seven. Okay. So there is also another variation. In the previous variation, it was said that you're given a perfect binary tree. That means every level definitely has two children, every parent. But this is a variation where it does not matter that every parent has two children. So if you see about it, 2 would be linked to 3, yes. 4 would be linked to 5. And then 5 should actually would have been linked to 6, but there is no child there. So 5 would directly be linked to the 7, right? So this is also a variation when it's not a perfect binary tree. So it looks like 4 would be linked to with sibling 5. 5 has to be linked to the cousin 6, but 6 is not there. So it will be linked to the next cousin or the 7. I'm just treating this like a family tree. You can solve this problem even without using a BFS or a DFS algo. But then in that case, both these variations would require different solutions. Take a step back, understand how you can solve this problem. And if you just see this diagram, then you know level wise, each node is just linked to the next node. So if you're able to process all the nodes in the level, then in that case, 2 should actually be linked to 3. 3 is null. 4 is linked to 5, 5 is linked to 6, 6 is linked to 7. If you process it by level, then it doesn't matter if it's a perfect binary tree or not. Let's get into the problem. As usual, I'm not getting into this part. I think at this point you would be familiar about the steps which is there. Now in the do BFS, we are having an outer loop to process the queue, and then you having an inner loop to iterate through the nodes in the queue. The only difference is that you will, as usual, iterate, process the nodes in the current level, and then add the children nodes also into the queue. And one more thing, what we are doing is we are having something called node previous. So we are storing the current node as previous before it gets overwritten. For example, if 3 is being processed, then in that case, in 2, 3 is being stored. Because, I'm sorry, if 3 is going to get processed, then 2 is stored as the previous, right? The same thing. If 5 is going to be processed, 4 is going to be stored as the previous. If 7 is processed, 5 is going to be stored as the previous. Why do we do it? So that if the previous is not equal to null, we can set the next of the previous to that of the current. Let's check it out here. So 1 would be there. Okay, and then at this point actually previous with starting would be null, so we can't do anything here. And then let's start from this point. 2, the previous would be null. Okay, when you come to 3, the previous would become 2, so therefore if previous is not null, so as previous is not null, 2 of next will become 3. That's it. So the same thing we will do for all the levels. So if you understand from this, it's kind of very easier for you to know how this processing actually happens, right? So both the variations of populating the next pointer can be solved just by having a previous node in extra, so that you store the previous node before the current gets overwritten, and then you link the previous nodes next to the current node. So classic level order traversal solves this purpose. Let's get to the next problem. If you ask me, how do you know all this problem can be solved by BFS? If you understand the BFS very clearly and then each problem, understand what the problem is asking, and then try to brainstorm multiple levels, and then you will be able to see a pattern that these are problems which can be solved by treating the nodes at every level. So you would know you would have to use a BFS at this point, and it's easy to use, right? So the key point here is to be very clear with the BFS ka template. That's it. Let's deep dive into this problem. Path sum. Given the root of a binary tree and an integer target sum, return true if the tree has a root to leaf path such that adding up all the values along the path equals the target sum. Okay, so what are they saying? Given the root of the binary tree and an integer target sum, return true if there is a path from the root to the leaf, if there is a target sum. If it's not there, then you don't have to, you can return false. So basically, what they're asking is if you sum up the values from the root to the leaf, any path is fine. And if that equals a target sum given, then in that case, it means there is a path sum. So basically, I can write this function as has path sum. So they're asking for the target sum is 22 and they want us to check if there was the sum from the root to the leaf. Okay. How can we solve this problem? We can definitely do this in BFS with a small tweak. How are we doing it? So what we are doing in this case is that when we insert a node to a queue, when we insert a tree node into the queue, instead of adding its value, we are changing its value from the target sum. For example, the root value, I'm doing 22 minus 5. So therefore it's 17. Instead of storing the root value as 5, I'm storing it as 22 minus 5, 17. That means what am I saying is that in the remaining part should just give me 17. That's all. Now we are going to do the BFS, classic BFS, outer loop to process the queue, inner loop to process all the nodes in the current level. Let me deal with this part. Before that, it's a classic BFS. So if the current of left is not null, what will we do? We'll add the current of left, the same thing for current of right. But before we are adding it, what are we doing? We are modifying the current value with the current of left value. For example, this one, how did we insert it? 22 minus 5 is 17. Now in this case, instead of having the value as 4, we would do 17 minus 4 as 13, 17 minus 8 is 9. Why are we doing that? I'll tell you. So you're doing 17 minus 4 is 13. Now at this point, what will you do? 13 minus 11 is 2. Then when you insert this, you will do 2 minus 7, which should be minus 4, minus 5. And then here you would do 2 minus 2, which is a 0. That means, once you reach the leaf node, if the value of the current node is 0, that means, there was a path sum. Else there was no path sum at all, right? So that's what we're doing. At every level, the only additional step we are doing is we are modifying the current node's value from the child's value. So basically, we are modifying the child's node value from the parent node. So how will this work? How will you know if it has a path sum or not? We are just going to check an additional check if it's a leaf node or not. If it's a leaf node, then we are checking if the current value is equal to 0. If it becomes 0, then we know there was a path sum. If it doesn't become 0, then we know there was no path sum. So now can you see I'm writing the isLeaf node function separately. You might feel like this is a very small function and why am I writing it separately? See, it's always wise to write each piece of code separately. There is a modularity and also it gives you the clarity of how you're solving the problems. So in the leaf node, we are checking what is a leaf node. If there is a current node and if its left is null and the right is null, that means it is a leaf node, right? So just writing the function. So if you might feel this problem as hard when you just saw it, but then if you see the solution, you'll feel like it's so easy that you're able to solve it. In this problem, right, there is a variation also. Here, what am I doing? I am subtracting the roots value or the current node's value at every level and then storing it. Instead of subtracting, you can also do it in addition. For example, how would you do it? Here you would store it as 5. Here you would store 5 plus 4, 9, 9 plus 11, 20, 20 plus 7, 27, 20 plus 2, 22. Then once you reach the leaf node, you will check if the value is equal to the target sum, right? That is also same way. So when you're doing subtraction, you will check if the leaf node is actually equal to 0 or not. And if you do by addition, you will check if the leaf node's value is equal to the target sum or not, right? Take a step back, process how we have just modified the template, and then understand. So before you cross the 4 problems, write down the template, understand how the template works, even write your template in your code editor, dry run it for a problem, debug it, like put a debugger, understand how it works for all the inputs so that you're very clear with it, and then you can build on top of it. So if you come to this point and then you're not very clear with the crux or the basic level or the traversal template, then you might find this all confusing. But then, if you understand that clearly, then all this becomes a cakewalk, right? Now let's get into the next problem. Symmetric tree. It's one of my favorite problem. It's also called as a mirror tree. Let's get into the problem. Given the root of a binary tree, check whether it is a mirror of itself, that is, symmetric around its center or not, right? Okay. So you're given a binary tree where you're given 1 and then 2, 3, 4, and then you're given 2, 4, 3. So if you see it here, it is something like 1, 2, 2, and then we have 3, 4, 3, 3, 4, 4, 3. That means it's symmetric because at every level it's same. 1 is there, okay. And then we have 2, 1, 2, match. If you see 3, 4, 3, 3, 3, 4, 4, 3, that means 3 and 3 is a match, 4 and 4 is a match. And therefore, you know, at every level it's symmetric, okay. If it was 3 4 3 4, then it's not a match. So basically, in a level, the end nodes should match and then the between nodes should match. Okay, right. So before we get to this, so we know just by seeing this, you would think it's a nice level order traversal, right? So if you do a level order traversal, what can you do? You can add all the elements to a list. We know we use and add all the elements to a list. Now, when you add elements to a list, you can check if the list is symmetric or not. How will you check? You can use an amazing two pointer and then use in the list if they both are equal. Yes, in a list if these both are equal, if they both are equal or not. So let's get to the part. So the classic function, what you have, a queue, a null check, add the root to the queue and call the BFS. So before we get to our queue, so assume that you write the normal BFS ka function where you have the outer queue, outer loop, which will process till the queue is empty. And then you will have the inner queue, which will process all the nodes in the current level. So after you add all the nodes which is present in the current level to a list, you're going to have a checklist. What is this going to function do? So you're going to have two pointers, one at the start and the other at the end of the list. And then till the start is less than n, we are going to check if the value at the start and end are equal. So at any point, if they are equal, if they are equal till the end of the list, then you know they are symmetric. For example, if the list was something like this, then you know it's symmetric. If at any point the symmetricity misses, then in that case, you know it's not symmetric. Okay. So if you see here, it's also actually a classic BFS only. But then there is an edge case. Think about this, okay? There is a loophole. Take some point, take some minutes, and then understand if you're able to describe what the loophole is. Pause the video at this point and then give a thought over 2 minutes and see where this particular logic, whatever we discussed till now, will fail. Why do we need an additional check types? Now let me go ahead with it. So according to the logic, what we thought, one will be in one set, true. And then if you take this tree, the next level would be 2 and 2. The next level would be 3 and 3, right? Right. So if you see this is a symmetric perfect, this is also symmetric perfect. This one will also be symmetric because in the list there'll be only 3 and 3 and there'll be a match. But this tree is not symmetric, right? Why? Because there was supposed to be a null here. So basically this tree should have been a null, 3, null and 3. And now when you do a 3 pointer, 3 and a null would not match and therefore it's not a symmetric tree. So you should be careful and understand that you have to process the null nodes. How do we do that? So this is a variation, just like how we had the list where we added all the elements to the list, and then we had just one variation to find the bottom leftmost where we pushed it to the left and right. The third variation is to use the null nodes. Usually when it's a null, we don't do anything, right? But then here, if it's a null, I'm going to add it to the list as well. Else it's the normal thing. You'll just add the left child, right child, and you'll also add the current of value to the list. It's the same thing what we did. Only thing additional in this case is that if the current is null, then in that case, we will actually add it to the queue. Why are we adding? You would have understood from the particular example we just discussed before. So this is a very good, interesting problem. And just by taking null into account, we are able to handle the edge case perfectly, right? Here again, take a moment and understand how the template has been modified to support the problem. Now, with that, we have come to the last problem of the session, serialize and deserialize a binary tree. Okay. Serialization is the process of converting a data structure or object into a sequence of bits. so that it can be stored in a file or memory buffer or transmitted across a network connection link to be reconstructed later in the same or another computer environment. So you would have to design an algorithm to serialize and deserialize a binary tree. There is no restriction on how your algorithm should work. You just need to ensure that a binary tree can be serialized to a string and this string can be deserialized to a original tree structure. Okay, let's try to understand. So if it's going to be 1, 2, 3, 4, 5, then when you serialize, it has to be 1, 2, and then here it will be none, none, right? Nothing. So you'll have a none, none, and then 3, 4, 5, and then when you deserialize, you need to get the same thing. Okay, I'm straight away diving into the function. So as usual, we are having a queue doing a null check for the root, adding the root, and then I'm also having a string buffer. Why? Because in Java, if you have a string, then the concatenation is a costly operation because the string is immutable. So in order to avoid that, I'm using a string buffer. So whenever the element is added to the queue or when you process it, you're also adding it to the string. So appending it to the string. So I'm appending the root value to the string. And then in that case, I'm just going to iterate through the nodes in the queue. So if it's a null, also it has to be taken care of. Why? If you don't take care of it, then when you reconstruct a tree, it will not be in the same way of how the tree was there before serialization. So just like the symmetric function, in this also, we are going to treat the null values. So if you find you are going to have an outer loop to process the queue and then inner loop to iterate the nodes in the queue or the current level, and then when you process the current queue and when you want to push its children, you're just checking if the current left is null. If it's a null, we are pushing the none. The same thing. If the current right is null, we are pushing a none. Else, as usual, we are just going to add the current of left to the queue, current of right to the queue. So in this case, because we need serialization, whenever an element is added to the queue, we are also adding it to the string buffer. The value of it is adding it to the string buffer. Right. That's it. And at last, we are going to return the string buffer. This is also very simple and a very slight modification when compared to a symmetric tree. So if you see the do BFS function of symmetric tree and this, there is a very slight modification. The only modification is that we are just appending it to a string. And the other thing is we are adding the values at every level to the string buffer. Right. So now that you have seen the serialization, let's get to the deserialization. So in deserialization, you would have to return the string to the as a tree node. So basically what are we doing? We are again having the classic null check, a queue. And then in this case, because it's a string, I'm using a split of method. So what is the split of method does is that it splits the string based on spaces and then stores it in an array. So basically, it splits the string based on space and stores, and therefore you would know the first element would be the root. We are creating a node. So in this case, what will we do is that as and when we go through or process through all the nodes in the queue, we will keep on creating tree nodes for it. So in the previous one, as and when we process, we actually added it to the string. Here from the string, we will create the tree nodes. Now let's get into the do BFS problem. We are having an outer loop to process the queue, inner loop to process iterate through the nodes in the queue, and then in this case we took the current value. Once you took the current value, I'm having in JS1 because the first one is already added as the root value, right? So you're going to process all the nodes in every level. So we're just going to check if the current value, if the n of j, right, whatever you split it, is actually not equal to null, then in that case, we are parsing the value. So we are converting the string to the integer. So we're doing an integer dot parsin. So when you want to convert an integer to string, you would use integer dot toString. And when you want to convert a string to an integer, then in that case, you'll use an integer dot parsin. This is specifically to Java. So basically, we are creating a tree node and then we are assessing at the left. If that was none, that means we know it had to be a null node. So we are just assigning it as null. So we are incrementing the pointer and the same thing we are doing for the right hand side. Why am I constructing left first and right first? Because Q is FIFO principle and then we go from level by level from left to right, left and then only right. So therefore we are constructing it in the same level. Don't be intimidated if you do not know Java. Just understand how this works and then you can code it in any language of your choice. Take a moment. This alone might be bit, a more of change when compared to all the other 7 problems you have seen. Take a moment, Try to understand this deeply, and then you will understand how simple this is also. Right. So, with that, guys, we have come to the end of the session. So, first things first, try to take a moment and then understand all the changes you made. Write down the template again and again. And now let's discuss the key takeaways. So, if somebody says BFS, you should right away know that you're using a queue. And then BFS is also called as a level order traversal. So there are three variations. The first three problems, what did we do? Level wise, we processed and stored it in a list. The second variation was for bottom leftmost tree, where we actually interchanged the pushing order into the inner queue to right to left. And then the third variation is to use a null insertion, right? So if you actually see, the only thing what kept changing throughout all these problems were processing the nodes only. So the only thing, lines of code changes, whatever you saw in blue, right, they are the ones which were changing for the BFS. So they were inside the do BFS. So only the thing which were processing the nodes in the current level actually kept changing. So if you see, the outer loop remained the same, only inside the inner loop it actually kept changing, right? That's because the only difference is there in the processing of the nodes in the inner level, right? So for all these solutions which you saw on the left, the time complexity is O of n, because we iterate through all the nodes, right? And the space complexity is also O of n, because in the worst case all would have to be stored into the queue. You can also say this as the time complexity. Some people would also say that it's actually equal to the height of the tree that we are processing all the nodes, right? So what is a very key takeaway? You should be very, very familiar with the key set template, and then just by modifying and tweaking the set template, you should be able to solve all these problems. So take these problems one by one, understand the template clearly, and then try solving it by your way. So with that, we wind up the session, and good luck for your learning.